Okay, so let's review. Okay, so at the very end, so at the very end, we did some conversions of statements, negating statements for the most part. But let's not forget that there are three operations that you could do. And so, as a summary, let me write this up in the abstract setting. So this is a statement or I see I'm in the wrong place. This is the right place. So as I was saying, we could the propositions. What can happen to the propositions is actually three things, and negation, contrapositive, and the converse. So that I want to summarize at least for the time being. So I'll put propositions here. Okay. So the original, I'm making it up. So say for any x there is a y, and say axy implies bxy. So we have seen examples of this already. The nature of xy is arbitrary, could be numbers, could be anything. A and b are once again propositions. They just depend on x and y. Okay, and we have an implication. So if a xy, then bxy. For example, once again, if we go back to example from Tuesday, a maybe two people are x bumped into y, and remember that was statement A, and B could be, I don't know, say x and y know each other. Okay, so then this statement says that every person on the train bumped into somebody. No, that's not what it say. There is somebody else. If they bumped into that person, they actually knew. That's what it says. It doesn't matter really. The point I'm making right now is to what we can do with these statements in an algebraic in kind of a mindless way, just like algebra sometimes works out. So if you know how to do long division, I have to ask you to close the.
Sorry, I'm just trying to pull up the notes.
So it's still not working?
No, we still have one page.
Well, you see that I got it. So
yeah,
hopefully it will work.
have you tried the shift reload?
Yeah, I just restarted my computer.
Oh, no, I mean the hard reload of the document should usually produce the new version of the document. If you just reload, it might give you the same thing. Okay, so mindless algebra is bad usually, but sometimes it just works out to your benefit. So if you have some certain skill, you do it almost without thinking. And if you did something with algebra at some point, and maybe in calculus also, maybe differentiation, well, same thing. Sometimes works with logic, and sometimes it doesn't, and you have to think hard. But when it does that, it is a nice shortcut. So I'm going with a contrapositive. So suppose this is statement A, their statement or proposition, let's call it P. Proposition P, and then the contrapositive is everything is the same except we have to, the statement should be equivalent to itself except the proposition would be turned around. So this is what it's going to be. XY, yeah, like this. So ignore what's the preamble, but what's inside of the parenthesis is equivalent to, it remains the same. So A implies B, it is the same as to say that not B implies not A. Okay, so once again, even if two numbers, what's the statement is? Yeah, the sum of two numbers is even, for example, then the negative is that it's not, but the implication is reversed. So we talked about that last time, so let me just stick to the summary. So these are equivalent. Equivalent meaning one thing, that is they are simultaneously true or simultaneously false, and there is no other option. So then the negation, remember the The difference is crucial because, I mean, negation is, well, certainly not equivalent, but rather it is mutually exclusive. They cannot be simultaneously true or simultaneously false. There is an x for any y, and here we negate the whole thing. So it will be, well, I'm not going to, there's really no way to do anything here. I'll just put not here, just that it's not applied. This certainly requires some extra work, and we already looked at it when we talked about the limit, which exactly has the same form as the original statement. For an x there is a y, for an epsilon there is a delta, and there's an implication at the end. And then I want to put a cross there to suggest that once again that picture should suggest to you that there is no reversal of the arrow when you do negation. Okay, so we just say that A does not imply B. What does it mean A does not imply B? Well, let's as an example, there's one more. So there were 4 items. But maybe this deserves a little bit of more time. So A does not imply B. What does it mean? Yeah?
Isn't it A and not B?
Say it again?
A and not B.
A and not B are not mutually exclusive. That's what you say. So it's possible, even though A is satisfied, there is still possibility that B is not satisfied. Okay? So that's what that doesn't apply mean. So it deserves extra attention. It depends on what's going on there. And I'll just see how in the next is the converse, and once again it reverses the arrow, but once again the negation does not reverse the arrow. So converse, it's the same statement once again, but this time the only thing that changes is that we reverse the arrow. Okay, so this is, it's better to remember these by examples. So if the original statement was the Pythagorean theorem, the converse is like the converse part of the Pythagorean theorem, which is also true. Okay, but then remember also examples when the statement, its converse is not true anymore. Okay, so mutually exclusive, and these two are not, the converse of P is not related to P directly, so they both could be wrong, both could be right, and so on. Or one right, one wrong. Okay, so all possible. So that's the summary. We're gonna once again, it's just a shortcut of what you can do algebraically in treating logic as algebra. Sometimes it doesn't work out. You just you acquire this ability to do it in your head gradually with practice. So that's what the rest of the semester will be used for. So this is just a starting point, and we'll be revisiting this all the time. Okay, so this time I want to actually talk about sets. And as we already have started with that, and a set theory approach is ubiquitous. So sets are, I'm not going to try to define sets. They are just collections of elements. So whatever that means. So element could be of any nature. It could be numbers, vectors, functions, sets. So you could collect set into sets. And I don't know, people, you can think of any other examples, as long as we can define, put them together in some particular way by either putting them on the list, that's the easiest way to do, or we are defining them through a property. So for example, this is the easiest way to define a set. So you already know what numbers are. You can just put some of them on the list, and that creates a set. So just keep in mind the notation. The set notation is very important. You may have seen it elsewhere, but so you're familiar with this. Just braces. which opens and closes a list of numbers, could be infinite, right? As long as it's clear what's included and what's not, you have defined a set. Okay, you could also define it through well, how about this? Now this is you might be also familiar with this notation. So with reals, say x is a real number and say x larger than 5. How about that? So that's a set notation. So once again, we indicate what we're talking about here. So maybe these are maybe numbers. So it's just like a setup, and then there's a condition that should be satisfied. So every number that satisfies this condition will be on the set. That does not satisfy will not be. Okay. So if the condition is unambiguous, then you have your set. Okay. And then so does this look familiar? This notation. Yeah. Okay. So we're going to use it a lot, and it is pretty much the language of mathematics. Okay. So what else we have already discussed? It is the unions and the intersections. Well, actually, let's start with subsets. So subsets of sets. So first of all, a subset is a set. Is a set to begin with. Okay, and secondly, it is how do you define a subset? You've heard the word subset? Well, I guess maybe we'll just start with examples instead. So for example, D is equal to x larger than 6. Okay, compare C and D.
What does it say under x is greater than 5 again?
It's condition.
Okay.
So as you can see, there are two, either one has a condition. So C includes all x's larger than 5, D includes all x's larger than 6. What's the relation between the two sets? C is a subset of D. Okay. Right. So in what sense? Meaning, what does it mean? I'm sorry, yes. So what, yeah, sorry about that. D is subset of D. D is subset of C. Okay, so what does it mean?
All elements in D are found in set C.
Right, yeah, all elements of D are elements of C. So that's a fine way to define a subset. In other words, D is a subset of of C. Okay, so let's however restate this in the spirit of what we have been doing. What? What are you doing? In the spirit of what we have been doing previously is this. This is a proposition, a statement. All elements of D are elements of C. So let's distinguish the two things. This is just the new language that we introduced. D is a subset of C, is the language that we introduce, which just allows us to speak easier of things. But it is accompanied by its definition. That's the definition. And it is a statement. So just to practice with it, in addition to this example, very simple example, how would we restate it? All elements of D are elements of C. Can you restate it in a more formal way, as we have discussed? Instead of all, what do we have usually? For every, right. So for every what?
Can you use element again, or do you have to use something else?
Say it again?
Can we use element again?
Yes, that's fine for now, yeah. For every element, say x of D, what?
Element of C.
X is an element of C. That's right. Okay, so that's one way to restate it in the form of this is I could write this part as a quantifier for any x in D. Well, by the way, you familiar with this symbol, right? So being an element of has this little. I think it may have coming from their exist term symbol, possibly, but I'm not sure. So anyway, so I could have restated it, and every time you know that you are putting in everything in a very precise way, if you can restate it, you don't have to, but if you can restate it in terms of the propositional logic with the preamble and statement, so this is the rest of the proposition. So x is a statement of C is a proposition, okay, that depends on x, and then it is preceded in the preamble by this little quantifier. Okay, there is another way. Can you restate it? Can you restate it in the form of an implication? Right. X an element of D implies X an element of C. Okay, so then you can see the match between the direction of the arrow and the direction of the in the implication and the direction of the inclusion symbol, D subset of C. Okay, so it's something we discussed last week. Okay. So that's the definition of a subset. It is all to take it very seriously because sometimes you have to. Sometimes sets are very large or complicated rather, and then saying that one is subset of the other requires you to do it carefully. And what is the usual way of proving that D is a subset of C? It is in fact. This is the method of proving, so most of the time that's how you do it. You pick an element in D and go through computations to demonstrate that it is also an element of C. For example, say, well, let's take it this way. Say D is the set of all. So I'm writing that once again in the language, and then we'll translate of all numbers divisible by 4. Okay? And C is the set of all numbers divisible by 2. Okay? The relation is a D is a subset of C, as we want to just demonstrate, but let's do it carefully. And use the set notation as well as the logic we have been using. So how do I write X? How do I write D in the set notation?
Braces,
Yeah.
X colon, and would it be
Well, but by the way, the notation is like this. If you want to have a more shorter way of writing it, is 4 bar X means 4 divides X. So this is really not satisfactory rather than just an abbreviation. So that's why I want to continue on and actually write out what it means. 4 divides X, or X is divisible by 4. What does it mean? That's right. X is equal to 4k for some integer k, Okay, I want to actually take it beyond this. Let's first of all, let's go on. 4K, thank you. 4K. Okay. For some integer k, let me do the same with 2, so we can, with the second, with c. So it's x, 2 divides x, or x is such that it is 2m. Make no mistake, don't try to use the same letter, that might mess you up. For some integer m. Okay, so that's fine. It is using words is fine, but sometimes if you want to really test how well you understand what's going on, write it out in a more abstract sense. So the set of numbers divisible by 4. Well, one thing is we haven't talked about. How do I translate this part? For some integer k. So x is equal to 4k for some integer k. So we can represent x as a k multiplied by 4. Okay, there is another way to do it. Can I bring this part over here? For some integer k. It's still somewhat informal language. If I want to make it formal, what do I do? Well, I try to use different language, that's what I'm driving at. If you just try to use slightly different language. So what we're saying is that we should be able to find such an integer k that x is over 4k. So what's the proper language for this? I can find k.
Are we using the same language that we just used above with the
Yeah.
green?
Yeah.
So you're going to say for every integer k?
No. There is. See, that's the thing. There is a k. There is a k such that x is equal to 4k. Okay, so you see that's the difference between the two. They're never to be confused. It's like black and white. They are opposite and they're pretty much don't overlap. So x is equal to 4k is for some k means that you can find k, in other words, or somebody else can find k, and what do we say? How do we say it? We say there is. There is. It's not literally searching for k, but we're saying that there is such a k that this equation is satisfied. Okay, similarly for c, x is equal to an integer such that there is let's assume all numbers are integers. There is such an m that x is equal to 2m. Okay? It's just a matter of translation and putting everything on a solid algebraic foundation. But now let's get to the point. Let's get to the point of demonstrating. So let's show that D is a subset of C. So once again, how do we do it? How take any x in D, show that x is in, I'm sorry, we start with D, show that x is in C. Okay? So what does it mean? It means that if x belongs to D, means that it satisfies the property of D. It belongs to C, it satisfies the property of C. So before we prove anything, maybe we should try to understand that part. So x belongs to D. X belongs to D is equivalent that there is a k such that x is equal to 4k. Okay? And now x belongs to C means, and we are talking about the same number, there is such an m that x is equal to 2m. Okay, so these are two statements or two propositions, one and the other. What is the relation between them that we want to demonstrate? What? No. No, the equality, but no. No, you equivalence means you go both ways.
D is a subset of C?
not the subset, but I'm talking about the implication. So D is a subset of D means that we have this implication. That's what we want to demonstrate. Okay, so the first condition implies the second, which will demonstrate that the first one, D, will be a subset of C. So remember this? We started this discussion with this. So D is a subset of D. D is a subset of C means that whatever restriction you impose on the elements of D implies the condition that you impose on the elements of C. And as you can see in practice, if you just look at the original statement, the restriction of C is looser. It is looser. It is easier to be divisible by 2 than by 4. Okay, so even before you get to prove it. But actually, once you work this out, the proof is easy, right? So prove it. Prove it. Okay, prove it. So the condition in the blue box implies the condition in the purple box. Okay, so how? So we start with, and that's how the proof actually works. So suppose X belongs to D, then there is, I don't have to use those letters necessarily, there is some K such that X is equal to 4K. Okay, let's work our way now towards the condition of C. So condition of C is in the purple box, so what I'm supposed to demonstrate that it is satisfied, I'm supposed to find M, or at least demonstrate that there is such an M. So what do I do? So X is given, it is not arbitrary, but suppose it's a given. Imagine that you're holding it in your hand. Then the condition of D is satisfied, which means that you also have K in your hand as well. So you have X here, you have K here, you have 4. That condition over there is satisfied, and you're supposed to work your way here somehow. So we need to find, not really a part of the proof, find M. What's M?
X divided by 2.
No.
I just brought M by itself.
Well, I guess nobody sees the answer yet. So we can just stop then, which happens all the time. If you still don't quite, you used all the logic in the world, maybe you understand logic perfectly, and yet if you don't quite understand the subject matter, you might still fail. So that's we did all the logic we could. We sorted everything out, but we still have to understand the numbers, the actual algebra here of divisibility in order to solve the problem. Fine. So then we have to insert here into the proof. We insert some analysis. So let's do analysis. So I'll stop here and write analysis. So X is equal to 4K, and at the same time it is equal to, look at it, 2M. So what? Remember, we're looking for M.
M is equal to 2K?
That's right. So choose M is equal to 2K. That's all. So K is an integer, so 2K is an integer, M is an integer, so we're fine. And we also know that X is equal to 2 times 2K. Okay, so there you go. It is 2M. There, done. Okay, so that was analysis. That is not technically part of the proof. That's how you discover the proof. And then with the logic and the proper use of the language, you write it out. So I try to write the proof in a very compact way. Well, sometimes it doesn't work out. And so, but now we know the answer, and we can complete the proof. So then we choose, what is it? The answer, M is equal to 2K. Then, so we continue this proof, which starts over there. So this is proof. Okay. Suppose X belongs to D, then there is some K such that integer X is equal to 4K. Then we we create a new number. How? By specifying what it is equal to. We don't know what K is, but it was given to us. Then we know what M is. So that M is equal to, that is another good word to use, let m is equal to 2k. Okay, so then what do we have here? X is equal to 4k. It is equal to 2 times 2k is equal to 2m, and m is an integer. Okay, so the condition of C is satisfied. So X belongs to C. Done. Okay. So even though we started with a condition and we tried to prove something about numbers, but just for the sake of an example, I converted the whole problem into a problem of sets and demonstrating one is a subset of the other. But you don't. That doesn't really solve the problem. You still have to go back to the actual algebra and figure out what's going on. So the proof is, well, this one, analysis, by the way, this is not part of the proof. So as you can see, once discovered, the proof is very simple. Or if not simple, it's certainly very short. So any questions about the proof? Okay, so what else? So these are the kinds of proof we're gonna see. Okay, now we're talking about unions and intersections. So unions and intersections. So I think I already have talked about that, but let's do it again. So the easiest way, the easiest place where you saw it previously is solving equations and especially inequalities. So remember, so let me do it again. So x minus 3 is between -1 and 1. Okay, so it's a double inequality. Let me do these two simultaneously. So x less than or equal to 3, or x is larger than 5. Okay, so it is a proposition. Once again, this is a proposition about x, but it's made of two propositions, and they are connected by this, what we call the conjunction. Remember this symbol. You can still use or, but you can use plain language as well. The point here is to convert this logical statement into a statement about sets. Okay, so X satisfies this property when what is the set, and it's really not. It's all right there. So X, let me put it this way: the set of solutions to the system of inequalities is, well, you don't have to do anything. You just write X and then have two conditions written out. Okay, so that's it. So there is everything. Solving equalities in equation inequality always is converted into statements about sets, because what you're after is a solution set. And so in a way we can say that we have found it, but really the point here is to realize that there are two inequalities and therefore there are two sets, right? So this is how we write it. One inequality, I take the solutions of the first inequality, x less than or equal to 3, and I take the solutions of the second inequality, which is x larger than 5, and then I combine them with the union symbol. So in other words, I have two sets, say A and B, and I create a new set. Okay? And you can see what happens. I certainly can draw it just as an illustration. 5. everything to the right of 5, and everything to the left of 3. So then once again this is A over here, and this is B over there. Okay, and we take the union, so we take all numbers, whether they belong to A or B, we combine them together in the new set. The language of OR is a bit controversial because in plain language, OR is often mutually exclusive. Okay, so in mathematics it is not. So not mutually exclusive.
What do you mean by mutually exclusive?
You go left or right. You cannot go simultaneously left and right. But if you are, as you can see, we take both of them. So either x is to the left or A, or to the right of 5, to the left of 3, to the right of 5. It doesn't matter. We take them both.
Okay.
Okay. So keep that in mind. It is indeed about union. So if we have two sets A and B, then when we take A or B, we're not excluding what's in the middle. Okay, we take the whole thing. So this is OR, union. Okay, so an example in a real life is cream or sugar. You could have both. But it is assumed that you say OR in plain language, and they will think that it is either one or the other. They have to be exclusive, and you cannot have both. Well, so not in mathematics, as you can see. This is how we do it. Okay, so now let's do the intersection, which is very similar, right? So it's certainly very easy to illustrate because this time we do take what they have in common. So this is the union. I'm sorry, the intersection. A intersection B. This one is the union. Okay. So the example you can think of well, if we go back to the example here, what is the specifically in this example A intersection B?
So shouldn't the symbols that you have in that set towards the bottom, should that be the upside down U instead of the U for that set at the bottom?
The on the right?
On the left where you circled A and B,
Yeah.
shouldn't it be an upside down U instead of the regular U since it's OR and not AND?
No, OR is up. The intersection is down.
Oh, okay, that's right.
I don't think there is any particular logic behind choosing one or the other.
Yeah.
I don't know. So there is really no way to remember it other than just remember it, just a symbol. So what's the intersection A and B on the left? Well, what is the intersection? It is illustrated on the right, but what we're talking about is by definition. So if it's not an example, then the definition is the elements that belong to both. So x, such that x belongs to A, and I'm using the other conjunction, x belongs to B.
How can that happen in a sense, since they're both not
Well, if you
overlapping?
well if you can put it in a. Can you put your question in the affirmative form? You said, how could it happen? Can you say it?
It can't happen?
It can happen, right. So if it can happen, then what's the conclusion?
That- Oh, I do it.
Well, so there are no such x. Has no elements. And the term we use for it is null set or the empty set. The empty set. Empty set. Null set is fine too. So A intersection B is empty. This is the symbol on the right. Okay, so certainly it doesn't have to be the case. So let me start over with two inequalities, and let me change 5 to 0. Okay, so I have the same problem as I started on the left, but I replace 5 on the one on the right with 0, and I replace OR with AND. Okay, so let me start over. So example, once again, x. So solve solve system of inequalities x less than or equal to 3, but this time it is and, or this conjunction, the hat, x larger than 0. Okay, so in that case, if you want to get ahead of yourself, so this is up to 3, and on one hand, that's the set on the left, the first inequality, and the first inequality, the second inequality is from 0 to infinity. Okay, so as you can see, there is an overlap, so we know what the answer is going to be there, but once again, the idea is to write it out in terms of sets. So there are two solutions. So solution is, of the first one is x less than or equal to 3, and solution for the second one, x larger than 0. Okay, so that's the second set. And then since there is an and between them, it has to satisfy x, the one we're after, has to satisfy both. That's what and is. And then the counterpart of the and statement in logic is the intersection in set theory. Okay, so that would be the answer one way or the other. Or the answer certainly probably, if you do it still doing algebra, you would probably write the answer in the form of an interval. But we don't really care about that. We're just trying to figure out ways of present things and just practice this logic as well as set theory. Let me do something else. Solve, say, x plus 1 is equal to 1, x minus y is equal to 2. Okay? So what does it mean to you? What does it mean to solve a system of two equations with two variables?
You get one of the variables by themselves and one of the problems and then plug in?
No, that's how you solve it.
Okay.
We don't know how to solve it. The problem we have to still know what we mean by to solve it. What does it mean to solve a system of two equations with two variables?
Find values for both variables that satisfy both equations.
That's right. So find all pairs. Don't ever forget the word all. Or all, because if we find one solution, there are infinitely many. That's a failure. So x squared equal to 1, you cannot say you have solved it if you say x equal 1, because then you lost minus 1. Anyway, so find all pairs xy such that they satisfy the equations. They satisfy the equations. So what does it have to do with the set theory? Well, so that's fairly clear. Let me just quickly wrap it up. So you remember what these are. Just take one at a time. X plus y equal 1. What is it? On the plane? Yeah, so what is it? Y equal 1 minus x is, it's a line. So both of these are lines, and what we're talking about is the solution is the intersection of these two lines. Okay, so we'll talk about that next time.